Picture this. Somewhere in the depths of space, an object lurks that could fundamentally rewrite everything we thought we knew about the most extreme phenomena in the universe. It's not a black hole, though it would appear identical to one from the outside. It's something far stranger, something that challenges the very foundations of physics itself. Tonight we're diving into one of the most unsettling concepts in modern astrophysics, a theoretical object so bizarre that it makes black holes seem almost mundane by comparison. Before we embark on this journey into the darkest corners of theoretical physics, I'd love to know where you're listening from and what keeps you fascinated by the mysteries of our cosmos. And if you find yourself drawn to these deep explorations of space and time, I'd be grateful if you gave this video a like and perhaps subscribe to join our community of cosmic wanderers. Get ready. The journey begins now. This is the story of Gravastars, and by the time we're finished tonight, you'll understand why some of the world's most brilliant physicists believe these hypothetical objects could be hiding in plain sight throughout our galaxy, masquerading as black holes, while harboring secrets that could revolutionize our understanding of reality itself. The year was 2001, and two physicists named Pavel Mazur and Emil Motola were grappling with one of the most troubling problems in modern science. Black holes, those cosmic monsters that devour everything in their path, contained within them a mathematical nightmare that had been haunting physicists for decades. At their hearts, according to Einstein's equations, lay singularities, points where matter compressed to infinite density, and the very laws of physics simply broke down. These weren't just minor inconveniences in the equations, they represented fundamental failures of our understanding of reality. How could the universe contain regions where mathematics itself became meaningless? How could physical laws that worked everywhere else simply cease to apply? And perhaps most disturbingly, if black holes could evaporate through Hawking radiation, what happened to all the information that had fallen into them? The equation suggested it would be lost forever, violating one of the most sacred principles of quantum mechanics. Mazur and Motola realized that something was profoundly wrong with this picture. The universe seemed too elegant, too mathematically consistent to harbor such fundamental contradictions. There had to be another explanation, another possibility that could account for the massive, compact objects we observe in space without requiring the existence of these problematic singularities. Their solution was as ingenious as it was unsettling. What if the objects we thought were black holes weren't black holes at all? What if they were something entirely different, something that could mimic black holes perfectly while avoiding all their theoretical problems? They called these hypothetical objects gravastars, a portmanteau of gravitational vacuum star, and their proposal would shake the foundations of astrophysics. A gravastar represents one of the most exotic concepts ever seriously proposed in physics. Imagine an object roughly the size of London, but weighing 10 times as much as our Sun. From the outside, it would appear identical to a black hole, bending light and space around it with devastating gravitational force. But inside, instead of a singularity where physics breaks down, something far stranger would lurk. The structure of a gravastar defies everything our intuition tells us about how matter should behave. At its core lies not compressed matter, but something called a gravitational vacuum condensate, a region of space where dark energy itself has condensed into a form of exotic matter that pushes outward with incredible force. This isn't the familiar matter that makes up stars and planets. This is something that exists in a quantum state similar to a Bose-Einstein condensate, where the very fabric of space-time has undergone a phase transition into something unprecedented. Surrounding this bizarre core is an ultra-thin shell of matter, so exotic that physicists have whimsically dubbed it galactic flubber. This shell would be incredibly dense, stronger than any material we can imagine, yet so thin that it would be virtually impossible to detect directly. The The shell serves as the boundary between the exotic interior and the normal space-time that surrounds the gravastar, creating a delicate balance between forces that want to expand and forces that want to collapse. The physics behind gravastar formation pushes the boundaries of what we think possible in the universe. When a massive star reaches the end of its life and begins to collapse, conventional theory tells us that gravity will eventually overcome all other forces, compressing the stellar core into a singularity and creating a black hole. But the gravastar hypothesis suggests that something far more dramatic might occur during this collapse. As the stellar material crashes inward with unimaginable violence, the extreme conditions might trigger a phase transition in the very nature of matter itself. Instead of forming a singularity, the collapsing material could undergo a transformation that turns it into a gravitational Bose-Einstein condensate, a state where quantum effects dominate on macroscopic scales. This would create a region of spacetime that wants to expand outward, filled with what physicists call de Sitter space, where the vacuum itself exerts negative pressure. The result would be a cosmic standoff of almost incomprehensible violence. The gravitational force of the stellar material wants to collapse everything into a point, but the exotic matter at the core pushes back with equal force, creating a stable configuration that could persist for billions of years. The thin shell that forms between these competing forces would be subjected to stresses beyond anything we can calculate, yet somehow it would hold, creating an object that appears from the outside to be a black hole, but internally represents a completely different kind of physics. This isn't just theoretical speculation divorced from observational reality. Gravastars could potentially explain some of the most mysterious phenomena we observe in the universe. The dark energy that appears to be accelerating the expansion of our entire cosmos might be intimately connected to the exotic matter that fills gravastar cores. If gravastars exist throughout the galaxy, they could represent reservoirs of dark energy, providing insights into the force that dominates the evolution of the universe itself. The implications extend far beyond individual stellar objects. If the gravastar hypothesis is correct, then every object we currently believe to be a black hole might actually be something far stranger. The supermassive objects at the centers of galaxies, the stellar mass compact objects we detect through gravitational waves, even the exotic phenomena we observe in the most violent regions of space, all of these could be gravastars rather than black holes. But here's what makes gravastars truly unsettling from an observational perspective. They would be virtually impossible to distinguish from black holes using current technology. A gravastar would bend light around itself in almost exactly the same way as a black hole. It would accumulate matter in an accretion disk that would glow with the same X-ray signatures we associate with black hole feeding. It would even emit Hawking radiation, that ghostly quantum mechanical process that causes black holes to slowly evaporate over cosmic time. The gravitational effects of a gravastar would be nearly identical to those of a black hole with the same mass. Stars orbiting around it would follow the same elliptical paths. Light passing near it would be bent and redshifted in the same characteristic patterns. Even the gravitational waves produced when two gravastars merge would sound almost identical to the chirps we detect when black holes collide, differing only in subtle details that might be at the very edge of our current detection capabilities. This observational degeneracy creates a profound uncertainty about the nature of the compact objects we study. When we point our telescopes at what we believe to be black holes, we might actually be looking at gravastars without knowing it. The distinction isn't merely academic, it represents a fundamental question about the nature of reality itself. The quantum mechanical properties of gravastars introduce possibilities that don't exist in traditional black hole physics. Unlike black holes, which trap information behind an event horizon, potentially forever, gravastars might allow information to escape through quantum mechanical processes occurring in their exotic matter shells. This could resolve the black hole information paradox that has plagued theoretical physics for decades, providing a mechanism for preserving the fundamental principle that information cannot be destroyed in quantum systems. The entropy of gravastars presents another striking contrast with black holes. While black holes must contain enormous amounts of entropy, according to thermodynamic principles, gravastars could have virtually zero entropy. This dramatic difference in their thermodynamic properties could have profound implications for how these objects interact with their environments and how they evolve over cosmic timescales. If gravastars exist in our galaxy, their presence would fundamentally alter our understanding of stellar evolution, galactic dynamics, and the large-scale structure of the universe. They could serve as laboratories for studying exotic states of matter that cannot be created or studied on Earth, providing insights into the behavior of quantum fields under extreme gravitational conditions. The theoretical framework that allows gravastars to exist represents a marriage between general relativity and quantum field theory, two pillars of modern physics that have proven notoriously difficult to unite. Gravastars emerge naturally from attempts to apply quantum mechanical principles to gravitational systems, suggesting that they might represent glimpses of a more complete theory of quantum gravity. Yet despite their theoretical elegance, gravastars remain hypothetical objects, with no confirmed observational evidence for their existence. The physics required for their formation involves extreme conditions and exotic matter states that push our understanding to its limits. The question of whether nature actually produces such objects remains one of the most intriguing open questions in modern astrophysics. As we stand at the threshold of a new era in observational astronomy, with gravitational wave detectors becoming more sensitive and space-based telescopes providing unprecedented views of the cosmos, we may finally have the tools necessary to distinguish between gravastars and black holes. The subtle differences in their gravitational wave signatures, their thermodynamic properties, and their interactions with surrounding matter could provide the smoking gun evidence that would confirm or rule out the existence of these exotic objects. The story of gravastars is far from over. In the laboratories and observatories around the world, scientists continue to refine the theoretical models, search for observational signatures, and debate the fundamental physics that could allow such objects to exist. Whether gravastars represent a genuine alternative to black holes or remain forever in the realm of theoretical speculation, they have already succeeded in forcing us to question our most basic assumptions about the nature of space, time, and matter in the extreme environments where gravity reigns supreme. The most unsettling aspect of the gravastar hypothesis isn't just that these objects might exist, but that they could fundamentally rewrite our understanding of how the universe operates at its most extreme scales. To grasp the true implications of this possibility, we need to delve deeper into the intricate physics that would govern these exotic objects and explore why their existence would represent far more than just another type of cosmic phenomenon. The three-region structure that defines a gravastar represents a delicate cosmic architecture unlike anything else theorized in astrophysics. At the very center lies what physicists call a false vacuum region, where the relationship between pressure and energy density takes on values that seem to defy common sense. In this core, pressure equals negative energy density, creating conditions where the vacuum itself pushes outward with tremendous force. This isn't empty space as we normally conceive it, but a region where the quantum fields that permeate all of reality have settled into an exotic state that generates repulsive gravitational effects. Surrounding this bizarre core is the infamous thin shell, a layer of matter so exotic that it exists in a state where pressure exactly equals energy density. This shell represents the boundary between two fundamentally different types of space-time geometry, and the physics required to maintain its stability pushes our theoretical understanding to its absolute limits. The matter composing this shell would need to possess properties unlike anything we observe in the natural world, existing in a perfect fluid state that can withstand gravitational stresses that would obliterate ordinary matter instantly. The outermost region consists of what physicists call true vacuum, where both pressure and energy density equal zero. This is the familiar empty space that surrounds normal astrophysical objects. But in the case of gravastars, this region would be profoundly affected by the exotic interior structure. The geometry of spacetime in this outer region would be nearly indistinguishable from that around a black hole, creating the observational mimicry that makes gravastars so difficult to detect. The quantum mechanical processes that would operate within gravastars introduce possibilities that stretch our understanding of fundamental physics. The core region would exist in a state analogous to a gravitational Bose-Einstein condensate, where matter has been cooled to such extreme conditions that quantum effects dominate on macroscopic scales. In normal Bose-Einstein condensates created in laboratories, atoms lose their individual identities and begin behaving as a single quantum entity. In the gravitational version proposed for gravastar cores, the condensate would involve the quantum fields of spacetime itself. This quantum state would create what physicists call de Sitter spacetime in the interior, a type of geometry where the expansion of space accelerates due to the presence of vacuum energy. The same physics that drives the accelerating expansion of our entire universe would be concentrated and contained within the gravastar core, creating a pocket of cosmic inflation trapped inside a stellar mass object. The implications of such a configuration extend far beyond the gravastar itself, potentially providing insights into the fundamental nature of dark energy and its role in cosmic evolution. The formation mechanism proposed for gravastars requires a sequence of events so extraordinary that it challenges our understanding of stellar collapse physics. When a massive star reaches the end of its nuclear burning phase, the conventional scenario involves the core collapsing until it reaches nuclear density, forming either a neutron star or continuing to collapse into a black hole. The gravastar hypothesis suggests that, under certain conditions, the collapse could trigger a phase transition that fundamentally alters the nature of matter itself. As the stellar core compresses beyond nuclear density, the extreme gravitational fields might induce a transition where ordinary matter transforms into the exotic quantum state required for gravastar formation. This process would involve temperatures and pressures so extreme that the very fabric of spacetime undergoes a structural change, similar to how water transforms into ice when cooled sufficiently, but operating at the level of quantum fields rather than molecular interactions. The energy scales involved in this transition would be staggering. The gravitational binding energy of a solar mass object, compressed to gravastar dimensions, approaches the total mass energy of the system itself. The process would release energy equivalent to the complete annihilation of several solar masses, yet somehow channel this energy into creating the stable exotic matter state that defines the gravastar structure. The physics governing this transformation remains largely speculative, representing one of the most challenging problems in theoretical astrophysics. Recent theoretical work has explored the possibility of nested gravastar configurations, sometimes called nestars, which could address some of the stability issues that plague the original gravastar model. These structures would consist of multiple shells of exotic matter separated by regions of de Sitter spacetime, creating a Russian doll-like arrangement that could be more stable against perturbations. The nested configuration would allow the extreme stresses to be distributed across multiple boundaries rather than concentrated in a single, infinitesimally thin shell. The mathematical description of nestars involves solving Einstein's field equations for configurations with multiple transitions between different types of matter and spacetime geometry. These solutions represent some of the most complex exact solutions to general relativity ever discovered, involving boundary conditions and matching requirements that push the limits of mathematical physics. The fact that such solutions exist at all suggests that the universe might harbour forms of matter organisation that we have barely begun to explore. The relationship between gravastars and dark energy represents one of the most intriguing aspects of the entire hypothesis. Dark energy, the mysterious force driving the accelerating expansion of the universe, remains one of the greatest puzzles in modern cosmology. We know it exists because we can observe its effects on cosmic expansion, but we have no direct way to study its properties or understand its fundamental nature. Gravastars could potentially serve as cosmic laboratories for dark energy research. If the cores of these objects truly contain vacuum energy in a condensed form, they would represent the only locations in the universe where we could study dark energy under controlled conditions. The physics operating within gravastar cores might provide insights into how dark energy behaves under extreme gravitational conditions and how it interacts with ordinary matter. The implications extend beyond individual objects to cosmological scales. If gravastars are common throughout the universe, they could represent a significant reservoir of dark energy that might influence cosmic evolution in ways we haven't yet considered. The formation and evolution of gravastars could be linked to the overall expansion history of the universe, creating feedback mechanisms between stellar-scale physics and cosmological dynamics. Some theoretical models suggest that the formation of gravastars might actually contribute to the accelerating expansion we observe. As massive stars collapse to form gravastars rather than black holes, they could be converting ordinary matter into dark energy, gradually increasing the total amount of vacuum energy in the universe. This process could provide a dynamic explanation for why cosmic acceleration appears to have begun relatively recently in cosmic history. The observational challenges posed by gravastars represent a fundamental limitation in our ability to test this hypothesis. The external spacetime geometry of a gravastar would be nearly identical to that of a black hole, with the same mass and angular momentum. This means that most observational techniques used to study compact objects would yield essentially the same results regardless of whether the object is a black hole or gravastar. However, subtle differences might exist that could eventually be detected with sufficiently sensitive instruments. The presence of a physical surface, even one as exotic as the gravastar shell, could create observational signatures that differ from the smooth event horizon of a black hole. Light interacting with this surface might produce spectral features or polarization patterns that could distinguish gravastars from their black hole counterparts. The thermal properties of gravastars present another potential avenue for observational distinction. While black holes have well-defined temperatures related to their surface gravity through the Hawking radiation mechanism, gravastars could have very different thermal characteristics. The exotic matter in the shell might emit radiation at different frequencies or with different spectral properties than the thermal radiation expected from black holes. Gravitational wave astronomy has opened new possibilities for testing the gravastar hypothesis. When compact objects merge, they produce gravitational waves that carry detailed information about their internal structure. The merger of two black holes creates a characteristic signal that includes three phases: the inspiral, merger, and ring-down. The ring-down phase, where the merged object settles into its final state, is particularly sensitive to the internal properties of the merging objects. Gravastar mergers would produce gravitational wave signals that differ subtly from black hole mergers, particularly in the ring-down phase. The presence of exotic matter shells and vacuum energy cores would create different vibrational modes than those of black holes, potentially producing detectable differences in the gravitational wave frequencies and damping rates. As gravitational wave detectors become more sensitive, they might be able to resolve these subtle differences and provide the first direct evidence for or against gravastar existence. The stability of rotating gravastars remains one of the most significant theoretical challenges facing the hypothesis. real astrophysical objects inevitably possess angular momentum, and any viable alternative to black holes must be stable against rotation. Early studies suggested that rotating gravastars might be unstable, developing instabilities that would cause them to collapse or explode. However, more recent theoretical work has identified parameter ranges where rotating gravastars could remain stable, at least over cosmological timescales. The rotation problem highlights the delicate balance required for gravastar stability. The exotic matter shell must maintain its integrity against both gravitational collapse and centrifugal forces that want to tear it apart. The physics governing this balance involves complex interactions between general relativistic effects, quantum field theory, and the equation of state of exotic matter. Small changes in any of these factors could determine whether a gravastar remains stable or undergoes catastrophic collapse. The question of gravastar formation in realistic astrophysical environments remains largely unsolved. While the mathematical solutions describing gravastars are elegant and well-defined, the physical processes that could create such objects during stellar collapse are poorly understood. The phase transition required to convert ordinary stellar matter into the exotic states needed for gravastar formation would need to occur under conditions of extreme temperature, pressure, and gravitational field strength. Current models of stellar collapse focus primarily on the nuclear physics governing neutron star formation and the general relativistic effects that lead to black hole formation. The additional physics required for gravastar formation would involve quantum field theory in curved spacetime, a domain where our theoretical understanding remains incomplete. The lack of a detailed formation mechanism represents a significant weakness in the gravastar hypothesis, making it difficult to predict when and under what conditions these objects might form. Despite these challenges, the gravastar concept continues to attract serious attention from theoretical physicists because it addresses fundamental problems that plague our current understanding of compact objects. The singularity problem in black hole physics represents more than just a mathematical inconvenience. It suggests that our theories break down precisely where we most need them to work. Gravastars offer a potential resolution to this crisis by eliminating singularities entirely while preserving most of the observable properties we associate with black holes. The information paradox presents another compelling motivation for considering alternatives to black holes. The loss of information that appears to occur when matter falls into a black hole conflicts with the fundamental principles of quantum mechanics, creating a paradox that has resisted resolution for decades. Gravastars, with their absence of event horizons and the possibility for information to escape through quantum processes in the exotic matter shell, could provide a natural solution to this paradox. The implications of confirming gravastar existence would extend far beyond astrophysics into the foundations of physics itself. The successful formation and observation of gravastars would represent the first direct evidence for exotic matter states predicted by quantum field theory in curved spacetime. This would validate theoretical approaches that attempt to unify general relativity with quantum mechanics, potentially pointing the way toward a complete theory of quantum gravity. The theoretical framework supporting gravastar existence reveals profound connections between the smallest and largest scales of physics, creating implications that stretch from quantum mechanics to cosmic evolution. As we delve deeper into these exotic objects, we encounter physics so strange that it challenges our most fundamental assumptions about the nature of reality itself. The quantum vacuum that would fill gravastar cores represents one of the most mysterious aspects of modern physics. Far from being empty space, the quantum vacuum seethes with virtual particles that pop into existence and annihilate each other in time frames so brief they exist below the threshold of direct observation. Under normal conditions, these quantum fluctuations average out to zero, creating the seemingly empty space we experience. But in the extreme gravitational environment of a gravastar core, these fluctuations could be amplified and stabilized into a macroscopic quantum state. The energy density required for this quantum vacuum condensation would be staggering. Physicists estimate that the vacuum energy inside a gravastar core would be approximately 10 to the 44th power times denser than the vacuum energy in ordinary space. This represents an energy concentration so extreme that it defies easy comprehension. To put this in perspective, if you could somehow extract a teaspoon of this condensed vacuum energy, it would contain more energy than all the stars in the observable universe. This extraordinary energy density would create gravitational effects unlike anything else in the known universe. The vacuum energy would exert negative pressure, literally pushing against the gravitational collapse that created the gravastar in the first place. This creates a cosmic standoff where the inward pull of gravity is exactly balanced by the outward push of quantum vacuum pressure, resulting in a stable configuration that could theoretically persist for timescales exceeding the current age of the universe. The mathematical description of this balance involves some of the most complex equations in theoretical physics. The stress-energy tensor that describes the matter content of the gravastar must satisfy Einstein's field equations while simultaneously incorporating the quantum mechanical properties of the vacuum state. These equations predict that the interior geometry would be fundamentally different from that of a black hole, featuring what physicists call de Sitter spacetime, where the curvature itself drives accelerating expansion. The boundary between the quantum vacuum core and the exotic matter shell would represent one of the most extreme interfaces in the universe. Here, the physics would transition from the expanding de Sitter geometry of the interior to the collapsing Schwarzschild geometry that would eventually characterize the exterior. This transition zone would be subjected to stresses that exceed anything we can model with current physics, requiring new theoretical frameworks to understand how such a boundary could remain stable. Recent advances in string theory and quantum gravity have provided new insights into how such exotic configurations might be stabilized. Some models suggest that extra dimensions of space could play a crucial role, allowing the extreme stresses to be distributed across higher dimensional geometries where they become more manageable. These higher dimensional effects could provide the additional stability needed to maintain the gravastar structure against the inevitable perturbations it would encounter in realistic astrophysical environments. The formation process for gravastars would require a sequence of phase transitions as exotic as anything proposed in cosmology. As a massive star collapses beyond the point where neutron degeneracy pressure can support it, the core would enter a regime where quantum gravity effects become dominant. The conventional wisdom suggests that nothing can stop the collapse at this point, leading inevitably to black hole formation. But the gravastar hypothesis proposes that the extreme curvature of spacetime could trigger a phase transition in the vacuum itself. This phase transition would be analogous to the symmetry breaking that occurred in the early universe, but concentrated into a region smaller than an atomic nucleus and occurring over timescales measured in fractions of a second. The vacuum would transition from its normal state to the exotic condensed state required for gravastar formation, releasing enormous amounts of energy in the process. This energy release could halt the collapse and create the outward pressure needed to stabilize the exotic matter shell. The thermodynamic properties of this transition present fascinating puzzles for theoretical physics. Unlike normal phase transitions, where entropy typically increases, the formation of a gravastar could actually decrease the total entropy of the system. The highly disordered collapsing stellar matter would be converted into the perfectly ordered quantum vacuum state, creating an entropy decrease that seems to violate the second law of thermodynamics. Resolving this apparent contradiction requires invoking subtle aspects of quantum mechanics and general relativity that remain poorly understood. The relationship between gravastars and dark energy extends beyond mere similarity in their equations of state. If gravastars exist throughout the universe, they could represent a distributed network of dark energy sources that collectively influence cosmic evolution. Each gravastar would act as a reservoir of vacuum energy, slowly leaking dark energy into the surrounding spacetime through quantum mechanical processes occurring at the exotic matter boundary. This leakage could provide a dynamic explanation for the observed acceleration of cosmic expansion. Rather than requiring a mysterious dark energy component that fills all of space uniformly, the acceleration could result from the cumulative effect of countless gravastars formed throughout cosmic history. As more massive stars collapse to form gravastars rather than black holes, the total amount of dark energy in the universe would gradually increase, naturally explaining why cosmic acceleration appears to have begun relatively recently. The implications for cosmic structure formation would be profound. Gravastars would interact gravitationally with surrounding matter in ways subtly different from black holes, potentially affecting the growth of galactic structures and the distribution of matter on large scales. The presence of dark energy reservoirs could create localized regions of accelerated expansion, influencing how galaxies cluster and evolve over cosmic time. Computer simulations attempting to model gravastar formation require some of the most sophisticated numerical techniques in theoretical physics. The calculations must simultaneously solve Einstein's field equations, track the quantum mechanical evolution of matter under extreme conditions, and model the hydrodynamics of stellar collapse. These simulations push current computational capabilities to their limits and often require simplifying assumptions that may not capture the full complexity of the physical processes involved. Early simulation attempts suggested that gravastar formation might be extremely rare, requiring very specific initial conditions and collapse trajectories. However, more recent work has identified broader parameter ranges where gravastar formation could be favored over black hole formation. The key appears to be the equation of state of matter at ultra-high densities, a regime where our understanding remains largely theoretical. The quantum field theory required to describe gravastar interiors involves concepts that stretch our understanding of fundamental physics. The vacuum condensate would exist in a state where quantum correlations extend across macroscopic distances, creating entanglement networks that could span the entire interior of the object. These quantum correlations could have observable effects, potentially allowing information to escape from the gravastar core through non-local quantum mechanical processes. The stability analysis of gravastars reveals a delicate dependence on parameters that we cannot currently measure or constrain observationally. Small changes in the equation of state of exotic matter or the strength of quantum corrections to general relativity could determine whether gravastars are stable over cosmological timescales or undergo rapid collapse. This sensitivity to unknown physics represents both the strength and weakness of the gravastar hypothesis. The potential observational signatures of gravastars continue to evolve as our theoretical understanding improves. Beyond the gravitational wave signatures we discussed earlier, gravastars could produce unique electromagnetic signatures through interactions between their exotic matter shells and infalling material. The quantum vacuum core could generate particle-antiparticle pairs through processes similar to Hawking radiation, but with spectral characteristics that differ from those expected from black holes. These particles would need to tunnel through the exotic matter shell to escape, potentially creating observable delays or modifications in the radiation spectrum. The shell itself could act as a filter, allowing certain types of particles to escape while trapping others, creating distinctive patterns in the emitted radiation that could serve as smoking gun evidence for gravastar existence. The magnetic field structure around gravastars would also differ from that around black holes. The presence of a physical surface, even one as exotic as the gravastar shell, could anchor magnetic field lines in ways that are impossible for black holes. This could affect how material accretes onto the object and how jets are launched from the accretion disk, potentially creating observable differences in the high-energy phenomena associated with these systems. The tidal effects experienced by objects orbiting close to gravastars would be subtly different from those around black holes. The modified space-time geometry in the vicinity of the exotic matter shell could create tidal patterns that deviate from the predictions of the Schwarzschild metric. These deviations would be extremely small and difficult to measure, but they represent potentially observable differences that could distinguish gravastars from black holes. The merger dynamics of gravastar binaries present particularly intriguing possibilities for gravitational wave astronomy. When two gravastars spiral together and merge, the collision of their exotic matter shells could create gravitational wave signatures, unlike anything predicted for black hole mergers. The shells might undergo partial disruption during the merger, creating complex oscillation patterns in the merged object that would produce distinctive gravitational wave emissions. These merger signatures could provide the most promising avenue for detecting gravastars observationally. The next generation of gravitational wave detectors will have the sensitivity needed to resolve the subtle differences between gravastar and black hole merger signals. If gravastars exist, their mergers should produce gravitational wave chirps with characteristic frequencies and damping patterns that differ measurably from black hole predictions. The implications for fundamental physics extend into the deepest questions about the nature of space and time. If gravastars exist, they would represent the first direct evidence that space-time itself can undergo phase transitions, changing its fundamental properties under extreme conditions. This would validate theoretical approaches to quantum gravity that treat space-time as an emergent phenomenon rather than a fixed background. The success of the gravastar hypothesis would also provide crucial insights into the black hole information paradox. The ability of information to escape from gravastar cores through quantum mechanical processes would demonstrate that the paradox results from incomplete understanding of black hole physics rather than fundamental inconsistencies in quantum mechanics. This resolution could guide the development of new theoretical frameworks for understanding quantum gravity and the nature of information in relativistic systems. The connection between gravastars and cosmology opens possibilities for understanding dark energy and cosmic acceleration through laboratory-scale physics. If we could somehow create and study gravastar analogues in controlled environments, we might gain insights into the fundamental nature of vacuum energy and its role in cosmic evolution. While creating actual gravastars in the laboratory remains far beyond current technology, theoretical studies of their properties could guide the development of new experimental approaches to dark energy research. The philosophical implications of gravastar existence would be equally profound. These objects would represent the ultimate synthesis of quantum mechanics and general relativity, demonstrating that the universe can create structures that embody the deepest principles of both theories simultaneously. The existence of such exotic objects would suggest that reality is far stranger and more wonderful than our current theories can fully capture. As we stand at the threshold of a new era in observational astronomy, with gravitational wave detectors reaching unprecedented sensitivity and space-based telescopes providing ever more detailed views of the cosmos, we may be approaching the moment when the gravastar hypothesis can be definitively tested. The subtle signatures that distinguish these exotic objects from black holes may soon be within reach of our most sophisticated instruments. The search for gravastars represents more than just another astronomical survey. It embodies our deepest quest to understand the fundamental nature of reality itself, pushing the boundaries of physics into regimes where quantum mechanics and gravity merge into something entirely new. Whether gravastars exist in nature remains an open question, but the very possibility of their existence has already transformed our understanding of what the universe might contain in its darkest and most extreme corners. The story of gravastars reminds us that the universe consistently proves stranger than our imagination. In the depths of space where gravity reigns supreme and quantum effects operate on cosmic scales, reality itself might be far more exotic than we have ever dared to suppose. These hypothetical objects represent the cutting edge of theoretical physics, where mathematics and observation converge to reveal possibilities that challenge everything we thought we knew about the cosmos. The quantum mechanical implications of gravastars extend into territories that challenge our most fundamental understanding of information and causality. Unlike black holes, where information appears to be trapped forever behind an event horizon, gravastars could allow quantum information to interact with the exotic matter shell in ways that preserve the fundamental principle of information conservation. The quantum correlations that would exist within the vacuum condensate core could create non-local connections that allow information to escape through mechanisms we're only beginning to understand. These quantum correlations would operate on scales far beyond anything we observe in laboratory physics. The entire interior of a gravastar would exist in a quantum superposition state, where the vacuum itself becomes a macroscopic quantum object. This would create entanglement networks spanning the diameter of the object, potentially allowing quantum information to tunnel through the exotic matter shell through processes that have no analogue in our everyday experience. The mathematical framework describing these quantum processes involves some of the most advanced concepts in theoretical physics. The wave function describing the gravastar interior would need to account for quantum correlations between vacuum fluctuations separated by stellar scale distances, creating computational challenges that push the boundaries of what we can model mathematically. These calculations suggest that gravastars could serve as natural quantum computers of unprecedented power, processing information through vacuum fluctuations in ways that could dwarf any artificial quantum system. The thermodynamic paradoxes associated with gravastar formation reveal deep connections between quantum mechanics, general relativity, and statistical mechanics. The second law of thermodynamics requires that entropy must increase during any physical process. Yet the formation of a gravastar appears to involve a dramatic decrease in entropy as chaotic stellar matter transforms into the perfectly ordered quantum vacuum state. Resolving this apparent contradiction requires invoking subtle aspects of quantum field theory in curved spacetime that remain at the cutting edge of theoretical research. Some theoretical models suggest that the entropy decrease during gravastar formation could be compensated by entropy increases in the surrounding spacetime geometry. The gravitational waves produced during the collapse process would carry entropy away from the system, potentially allowing the total entropy to increase even as the local entropy decreases within the gravastar itself. This mechanism would preserve the second law of thermodynamics, while allowing for the exotic entropy properties that make gravastars theoretically possible. The relationship between gravastars and cosmic inflation presents one of the most intriguing aspects of the entire hypothesis. The de Sitter spacetime that characterizes gravastar interiors is mathematically identical to the spacetime that drove the exponential expansion of the early universe during the inflationary epoch. This suggests that gravastars could represent fossil remnants of cosmic inflation, trapped and preserved within stellar mass objects scattered throughout the galaxy. If this connection is real, then studying gravastars could provide unprecedented insights into the physics of cosmic inflation. The processes that drove the exponential expansion of the early universe would be accessible to direct observation within gravastar cores, allowing us to test theories of inflation that are otherwise beyond experimental reach. The quantum fluctuations that created the seeds of cosmic structure during inflation could be preserved and amplified within gravastar interiors, creating observable signatures that could reveal the fundamental physics of the universe's earliest moments. The gravitational field equations that describe gravastar spacetime geometry involve solutions to Einstein's equations that push the mathematical formalism to its limits. These solutions require careful matching of different spacetime geometries across the exotic matter shell, creating boundary conditions that must be satisfied with extraordinary precision. The mathematics reveals that gravastars exist in a narrow parameter space where the competing forces of gravitational collapse and quantum vacuum pressure achieve perfect balance. Small deviations from this precise balance could lead to catastrophic instability. If the vacuum energy density becomes too large, the gravastar could explode outward in a cosmic inflation event that would expand at light speed, potentially consuming everything in its path. If the vacuum energy becomes too small, the quantum pressure would be insufficient to halt gravitational collapse, and the object would revert to forming a conventional black hole. The stability requirements are so stringent that some physicists question whether gravastar formation could ever occur in realistic astrophysical environments. The observational signatures that could distinguish gravastars from black holes continue to evolve as theoretical understanding advances. Beyond gravitational waves and electromagnetic radiation, gravastars could produce unique signatures in cosmic ray interactions. High-energy particles colliding with the exotic matter shell could produce shower patterns unlike anything observed from black hole environments, potentially creating detectable differences in the cosmic ray spectrum from regions containing gravastars. The magnetic field structures around gravastars would differ fundamentally from those around black holes. The presence of a physical surface, even one composed of exotic quantum matter, could anchor magnetic field lines and create stable configurations impossible in black hole magnetospheres. These magnetic structures could affect how charged particles accelerate in the vicinity of gravastars, potentially producing distinctive patterns in radio and X-ray emissions that could serve as observational fingerprints. The tidal disruption events that occur when stars venture too close to compact objects could provide another avenue for distinguishing gravastars from black holes. The modified spacetime geometry near the exotic matter shell could create tidal patterns that differ subtly from black hole predictions. These differences would be most pronounced for stars that approach very close to the gravastar surface, where the effects of the exotic matter shell would be most significant. The implications for galaxy formation and evolution could be profound if gravastars prove to exist in significant numbers. The dark energy reservoirs contained within gravastar cores could influence the large-scale structure of the universe in ways that have not been considered in current cosmological models. Regions with high concentrations of gravastars could experience enhanced cosmic expansion, affecting how galaxies cluster and evolve over cosmic time. The feedback mechanisms between gravastar formation and cosmic evolution could create complex dynamics that link stellar-scale physics to cosmological scale phenomena. As more massive stars collapse to form gravastars rather than black holes, the total amount of dark energy in the universe would gradually increase, potentially explaining the observed acceleration of cosmic expansion without requiring mysterious dark energy components that fill all of space uniformly. Computer simulations attempting to model these large-scale effects face enormous computational challenges. The calculations must track the formation and evolution of individual gravastars while simultaneously modeling their collective influence on cosmic structure formation. These simulations require incorporating physics across an enormous range of scales, from quantum mechanics operating within gravastar cores to general relativistic effects governing cosmic expansion. The quantum field theory describing gravastar interiors involves concepts that extend far beyond our current experimental reach. The vacuum condensate state would involve quantum coherence effects operating across macroscopic distances, creating conditions where the boundary between quantum and classical physics becomes meaningless. These effects could produce observable consequences through their influence on light and matter passing through the gravastar's gravitational field. The polarization of light propagating through the curved spacetime around gravastars could carry signatures of the exotic quantum states within the core. Quantum vacuum birefringence effects could create distinctive polarization patterns that differ from those predicted for black holes. These subtle differences would require extremely sensitive polarimetry measurements to detect, but they could provide definitive evidence for the exotic matter states that define gravastar physics. The particle physics implications of gravastar existence would extend into the deepest questions about the fundamental nature of matter and energy. The exotic matter composing the gravastar shell would represent a new state of matter that exists nowhere else in the known universe. Understanding the properties of this matter could provide insights into the unification of fundamental forces and the ultimate structure of reality. The phase transitions required for gravastar formation could involve physics beyond the standard model of particle physics. The extreme conditions during stellar collapse could activate new symmetries and force unification mechanisms that are normally hidden at lower energy scales. Studying gravastars could thus provide a natural laboratory for exploring physics that would otherwise require particle accelerators far beyond current technological capabilities. The relationship between gravastars and dark matter presents another intriguing possibility. Some theoretical models suggest that dark matter particles could accumulate within gravastar cores, where they would interact with the exotic vacuum state in novel ways. These interactions could produce observable signatures that could reveal the nature of dark matter, while simultaneously providing evidence for gravastar existence. The cosmological constant problem, one of the most severe fine-tuning issues in modern physics, could potentially be addressed through gravastar physics. The vacuum energy density required for gravastar formation is enormous compared to the tiny cosmological constant that characterizes our universe's expansion. Understanding how this energy is contained and controlled within gravastars could provide insights into why the cosmological constant is so much smaller than naive quantum field theory predictions suggest. The stability analysis of gravastar configurations reveals a complex landscape of possible solutions to Einstein's equations. Beyond the original Maser-Mottola model, theoretical physicists have discovered families of gravastar solutions with different internal structures and stability properties. Some of these configurations could be more stable against rotation and perturbations, potentially making them more realistic candidates for naturally occurring objects. The nested gravastar or nestar configurations represent particularly intriguing possibilities for enhanced stability. These Russian doll-like structures could distribute the extreme stresses across multiple boundaries, making the overall configuration more robust against the inevitable perturbations that would affect real astrophysical objects. The mathematical complexity of these solutions challenges our computational capabilities, but they suggest that nature might have multiple pathways for creating stable exotic objects. The energy extraction mechanisms from gravastars could differ fundamentally from the Penrose processes that allow energy extraction from rotating black holes. The presence of a physical surface and exotic matter shell could enable new mechanisms for tapping into the enormous energy reservoirs contained within gravastar cores. These processes could have implications for advanced civilizations capable of manipulating such extreme objects, though the engineering challenges would be beyond anything currently imaginable. The gravitational lensing properties of gravastars would create subtle but potentially detectable differences from black hole lensing. The modified spacetime geometry near the exotic matter shell could produce caustic patterns and magnification distributions that differ from black hole predictions. These effects would be most pronounced for lensing configurations, where light rays pass very close to the gravastar surface, where the influence of the exotic matter would be strongest. The merger dynamics of gravastar binaries could produce some of the most complex gravitational wave signals ever predicted. The collision and potential disruption of exotic matter shells could create multi-stage merger processes with characteristic frequencies and evolution patterns that have no analogue in black hole mergers. The post-merger oscillations could persist for much longer than the ring-down signals from black hole mergers, providing extended observation windows for detailed gravitational wave analysis. The implications for tests of general relativity could be profound if gravastars exist and can be observationally distinguished from black holes. These objects would provide natural laboratories for testing Einstein's equations under conditions of extreme curvature and exotic matter content. Any deviations from general relativistic predictions could point toward new physics or modifications to gravity that become important under these extreme conditions. The quantum gravity implications of gravastar physics touch on the most fundamental questions about the nature of space and time. The successful formation and stability of gravastars would demonstrate that space-time can undergo phase transitions, changing its fundamental properties under extreme conditions. This would validate approaches to quantum gravity that treat space-time as an emergent phenomenon rather than a fixed background. The holographic principle, which suggests that all information in a volume of space can be encoded on its boundary, could take on new meaning in the context of gravastar physics. The exotic matter shell could serve as a holographic screen that encodes information about the quantum vacuum state within the core, potentially providing new insights into how information is stored and processed in gravitational systems. The connection between gravastars and string theory remains largely unexplored, but could prove crucial for understanding whether these objects can actually form in nature. String theory provides frameworks for understanding exotic matter states and higher dimensional physics that could stabilize gravastar configurations. The extra dimensions predicted by string theory could provide additional degrees of freedom that allow the extreme stresses within gravastars to be managed in ways impossible in ordinary four-dimensional spacetime. The experimental implications of gravastar physics extend beyond astronomy into laboratory science. While we cannot create actual gravastars in terrestrial laboratories, we might be able to create analog systems that capture some of their essential physics. Bose-Einstein condensates in atomic gases could potentially simulate aspects of the quantum vacuum state that characterizes gravastar cores, providing testable predictions for how such exotic matter behaves under various conditions. The philosophical implications of gravastar existence would challenge our understanding of the relationship between mathematics and physical reality. These objects emerge naturally from the mathematical formalism of general relativity and quantum field theory, yet they require physics so exotic that their actual existence seems almost impossible. If gravastars do exist, they would demonstrate that the universe can realize even the most mathematically exotic solutions to our physical theories. As we continue to probe the deepest mysteries of the cosmos, the gravastar hypothesis stands as a testament to the power of theoretical physics to reveal possibilities that stretch our imagination. Whether these exotic objects actually exist in nature remains an open question that may be answered by the next generation of gravitational wave detectors and space-based telescopes. But regardless of their ultimate fate, gravastars have already succeeded in expanding our conception of what the universe might contain in its most extreme and mysterious corners, where the laws of physics themselves undergo transformations as profound as any we have yet discovered. The search for observational evidence that could finally settle the gravastar debate has led astronomers to examine some of the most extreme environments in our galaxy with unprecedented scrutiny. The supermassive object at the center of our own Milky Way, known as Sagittarius, a star, has become a prime target for this investigation. This 4 million solar mass monster sits just 26,000 light-years away, close enough that we can observe individual stars orbiting around it with remarkable precision. For decades, astronomers have assumed that Sagittarius A star is a black hole based on its enormous mass concentrated into such a small region of space. But the Gravastar hypothesis forces us to reconsider this assumption. If Sagittarius A star were actually a gravastar, it would appear virtually identical to a black hole from our perspective, exhibiting the same gravitational effects on nearby stars and producing the same energetic phenomena as matter spirals inward toward its surface. The event horizon. Telescope's historic image of the shadow around Sagittarius A star provides tantalizing clues, but these observations remain consistent with both black hole and gravastar interpretations. The dark region in the center of the image could represent either the event horizon of a black hole or the gravitationally redshifted surface of a gravastar. The distinction lies in subtle details that push current observational capabilities to their absolute limits. Recent theoretical work has identified specific observational signatures that could distinguish between these possibilities. The polarization patterns of light emerging from the accretion disk around Sagittarius A star could carry information about the underlying object's nature. A gravastar's exotic matter shell might interact with electromagnetic radiation in ways that create distinctive polarization signatures, different from those expected around a black hole's event horizon. The timing of X-ray flares from material falling towards Sagittarius A star provides another potential avenue for discrimination. These high-energy outbursts occur when clumps of matter in the accretion disk heat up as they spiral inward. The precise timing and spectral characteristics of these flares depend on the gravitational field structure very close to the compact object. A gravastar's modified spacetime geometry could produce timing patterns that deviate subtly but measurably from black hole predictions. The stellar orbits around Sagittarius A star offer perhaps the most promising opportunity for detecting gravastar signatures. The star designated S2 completes an elliptical orbit that brings it within just 120 astronomical units of the central object every 16 years. At its closest approach, this star experiences gravitational effects so extreme that general relativistic corrections become clearly observable. If Sagittarius A star were a gravastar rather than a black hole, the star's orbital motion would deviate from black hole predictions in ways that could be detectable with current astrometric precision. The exotic matter shell of a gravastar would create additional gravitational perturbations that could shift the star's perihelion advance by amounts measurable with interferometric techniques. These deviations would accumulate over multiple orbits, potentially providing definitive evidence for or against the gravastar interpretation. The implications of discovering that Sagittarius A star is actually a gravastar would revolutionize our understanding of galactic evolution. The dark energy reservoir contained within such a massive gravastar could influence the dynamics of our entire galaxy in ways we have never considered. The slow leakage of vacuum energy from the galactic center could create large-scale flows that affect star formation rates and the distribution of matter throughout the Milky Way. The formation history of such a massive gravastar presents profound puzzles for stellar evolution theory. Unlike stellar mass gravastars that could form from individual collapsing stars, supermassive gravastars would require formation mechanisms that operate on entirely different scales. Some theoretical models suggest that they could form during the early universe through the direct collapse of primordial gas clouds, while others propose that they could grow through the accretion and merger of smaller gravastars over cosmic time. The quantum mechanical properties of supermassive gravastars would be even more exotic than their stellar mass counterparts. The quantum coherence effects within the vacuum condensate core would operate across scales comparable to our solar system. creating entanglement networks of unprecedented complexity. These macroscopic quantum effects could produce observable consequences through their influence on the surrounding space-time geometry and electromagnetic fields. The energy scales involved in supermassive gravastar physics would approach those present during the earliest moments of cosmic history. The vacuum energy density within the core of a million solar mass gravastar would rival that which drove cosmic inflation, potentially creating connections between galactic scale physics and cosmological evolution that we are only beginning to explore. Recent advances in gravitational wave astronomy have opened new possibilities for testing the gravastar hypothesis through observations of extreme mass ratio inspirals. These events occur when stellar mass objects spiral into supermassive compact objects, producing gravitational waves that carry detailed information about the space-time geometry in the strong field regime. The LISA space-based gravitational wave detector, planned for the 2030s, will have the sensitivity needed to observe these systems and distinguish between black hole and gravastar signatures. The gravitational wave signals from extreme mass ratio inspirals around gravastars would differ from black hole predictions in characteristic ways. The presence of the exotic matter shell would create additional resonances and mode couplings that would modify the gravitational wave frequency evolution. These effects would be most pronounced when the inspiraling object passes very close to the gravastar surface, where the influence of exotic matter would be strongest. The theoretical framework describing these gravitational wave signatures involves some of the most sophisticated calculations in mathematical physics. The equations must account for the self-force effects as the small object back-reacts on the gravastar's space-time geometry, the tidal perturbations created by the exotic matter shell, and the complex mode mixing that occurs when gravitational waves propagate through the modified geometry near the surface. Computer simulations of these systems require numerical relativity codes adapted to handle the exotic matter distributions that characterize gravastars. The computational challenges are enormous, as the calculations must resolve physics across multiple scales simultaneously, from the quantum mechanical properties of the vacuum condensate to the large-scale gravitational wave propagation through the surrounding space-time. The observational prospects for detecting gravastar signatures through extreme mass ratio inspirals depend critically on the rate at which these events occur. Current estimates suggest that LISA could observe dozens to hundreds of such events per year, providing a statistical sample large enough to distinguish between different theoretical models. The precision required for this discrimination pushes gravitational wave astronomy into a new regime where subtle relativistic effects become the primary observational target. The implications for fundamental physics extend beyond tests of general relativity into probes of quantum gravity and the nature of spacetime itself. The successful observation of gravastar signatures in gravitational waves would provide the first direct evidence for macroscopic quantum effects in strongly curved spacetime, validating theoretical approaches that treat gravity as an emergent phenomenon arising from more fundamental quantum processes. The connection between gravastars and dark energy research has motivated new experimental approaches to understanding vacuum energy properties. Laboratory experiments using ultra-high-intensity laser pulses can create conditions where quantum vacuum effects become observable, potentially providing insights into the physics that governs gravastar cores. These experiments probe the nonlinear response of the quantum vacuum to strong electromagnetic fields, revealing aspects of quantum field theory that could be relevant for understanding exotic matter states. The Casimir effect, where quantum vacuum fluctuations create measurable forces between closely spaced conducting plates, provides a terrestrial analogue for some aspects of gravastar physics. Recent precision measurements of Casimir forces under various geometric configurations have revealed subtle deviations from theoretical predictions, suggesting that our understanding of vacuum energy remains incomplete. These discrepancies could point toward new physics that becomes important in the extreme environments that would exist within gravastar cores. Theoretical investigations of gravastar stability have revealed a rich landscape of possible configurations, each with its own unique properties and observational signatures. Beyond the original spherically symmetric models, researchers have explored rotating gravastars, charged gravastars, and configurations with multiple exotic matter shells. Each variant presents its own challenges for stability analysis and observational detection, but they collectively expand the parameter space where gravastar-like objects could potentially exist. The mathematical techniques required for these stability analyses draw from diverse areas of theoretical physics, including perturbation theory, dynamical systems analysis, and numerical relativity. The calculations must account for both radial and non-radial perturbations, as well as the coupling between gravitational, electromagnetic, and exotic matter degrees of freedom. The results reveal that stability depends sensitively on the equation of state of exotic matter and the precise values of physical constants, suggesting that gravastar formation might require very specific conditions to occur in nature. Recent work on gravastar thermodynamics has revealed surprising connections to black hole physics despite their fundamental differences. While gravastars lack event horizons, they can still exhibit thermal properties through quantum processes occurring at the exotic matter boundary. The temperature associated with these thermal effects could be related to the surface gravity of the gravastar, creating an analogue to the Hawking temperature of black holes, but with potentially different spectral characteristics. The entropy of gravastar configurations presents particularly intriguing puzzles for statistical mechanics. Unlike black holes whose entropy is proportional to their surface area, gravastars could have entropy that depends on their internal structure and the quantum state of the vacuum condensate core. Understanding these entropy relationships could provide insights into the fundamental nature of information storage in gravitational systems and the ultimate limits on computational processes in strongly curved spacetime. The relationship between gravastars and cosmic inflation has inspired new theoretical frameworks that attempt to unify stellar scale and cosmological scale physics. Some models propose that gravastar formation could trigger localized inflation events that create bubble universes connected to our own through wormhole-like structures. While highly speculative, these ideas illustrate how gravastar physics could connect to the deepest questions about the nature of reality and the possible existence of multiple universes. The implications for astrobiology present another fascinating dimension to gravastar research. If gravastars exist and can be distinguished from black holes, they could serve as natural laboratories for studying the behavior of matter and energy under conditions that have no terrestrial analogue. The exotic physics operating within gravastar cores could provide insights into alternative biochemistries and information processing mechanisms that might be relevant for understanding the possibilities and limitations of life in the universe. The technological implications of confirmed gravastar existence would be profound for any sufficiently advanced civilization. The enormous energy reservoirs contained within gravastar cores could theoretically be tapped through mechanisms that have no analogue in black hole physics. The exotic matter states that stabilize gravastars could provide templates for creating new materials with unprecedented properties, though the engineering challenges would be far beyond anything currently imaginable. The philosophical implications extend into questions about the nature of mathematical truth and physical reality. Gravastars emerge naturally from the mathematical formalism of general relativity and quantum field theory, yet they require physics so exotic that their existence seems almost miraculous. If nature has indeed found ways to realize these mathematical possibilities, it would suggest a deep connection between abstract mathematical structures and physical reality that we are only beginning to comprehend. The observational campaigns designed to search for gravastar signatures represent some of the most ambitious projects in modern astronomy. The coordination required between gravitational wave detectors, radio telescopes, X-ray observatories, and optical interferometers pushes the boundaries of international scientific collaboration. These multi-messenger approaches to gravastar detection could serve as templates for future investigations of other exotic phenomena predicted by theoretical physics. The data analysis challenges posed by gravastar searches require new computational techniques that can extract subtle signals from noisy astronomical datasets. Machine learning algorithms trained on theoretical gravastar models could potentially identify patterns that human analysts might miss, but these approaches must be carefully validated to avoid false positive detections. The statistical techniques required for claiming a gravastar discovery would need to meet the most rigorous standards of scientific evidence. The educational implications of gravastar research extend into inspiring new generations of physicists and astronomers to pursue careers in fundamental science. The exotic nature of these objects captures the imagination while simultaneously requiring mastery of the most advanced concepts in modern physics. Gravastar research thus serves as a bridge between abstract theoretical physics and observational astronomy, illustrating how mathematical predictions can guide experimental investigation. The international nature of gravastar research has fostered collaborations that transcend national boundaries and cultural differences. The shared quest to understand these exotic objects has created scientific partnerships that could serve as models for addressing other global challenges. The purely intellectual nature of the questions involved demonstrates the power of basic scientific research to unite humanity in common purpose. The timeline for resolving the gravastar question depends on advances in observational technology that are already under development. The next generation of gravitational wave detectors will have sensitivity improvements that could definitively distinguish gravastar signatures from black hole predictions. Space-based telescopes with unprecedented resolution could detect the subtle electromagnetic signatures that differentiate these exotic objects from their conventional counterparts. The theoretical framework supporting gravastar physics continues to evolve as new insights emerge from quantum gravity research and cosmology. String theory, loop quantum gravity, and other approaches to unifying general relativity with quantum mechanics all provide different perspectives on whether gravastar-like objects could actually form in nature. The convergence or divergence of these theoretical predictions could provide crucial guidance for interpreting future observations. The implications for our understanding of cosmic evolution could be revolutionary if gravastars prove to exist in significant numbers throughout the universe. The dark energy reservoirs they contain could influence structure formation on scales from individual galaxies to the cosmic web itself. The feedback between gravastar formation and cosmic expansion could create complex dynamics that link the physics of stellar collapse to the ultimate fate of the universe. As we stand at the threshold of discoveries that could fundamentally alter our understanding of the cosmos, the gravastar hypothesis serves as a reminder that the universe consistently proves stranger than our imagination. In the depths of space, where quantum mechanics and general relativity merge into something entirely new, reality itself might harbor possibilities that challenge our most basic assumptions about the nature of matter, energy, and space-time. The search for these exotic objects continues in observatories around the world, where dedicated researchers probe the darkness between the stars for signs of physics beyond our current understanding. Whether gravastars exist or remain forever theoretical, they have already succeeded in expanding our conception of what the universe might contain in its most mysterious and extreme corners, where the laws of nature themselves undergo transformations as profound as any we have yet discovered. The quiet revolution in our understanding of compact objects unfolds not with dramatic announcements, but through the patient accumulation of observational evidence and theoretical insights that slowly reveal the true nature of these cosmic enigmas. In this careful process of scientific discovery, we edge closer to answering fundamental questions about reality itself, guided by mathematics toward truths that may prove more extraordinary than we have ever dared to imagine. The quest to identify gravastar signatures has pushed observational astronomy into uncharted territories where the subtlest deviations from theoretical predictions could reveal the most profound truths about cosmic architecture. The challenge lies not in finding obvious differences, but in detecting whisper-quiet variations that speak to the fundamental nature of space-time itself. Consider the intricate dance of light around these hypothetical objects. When photons climb out of a gravastar's gravitational well, they would experience redshift patterns that differ microscopically from black hole predictions. The exotic matter shell would create additional gravitational potential steps that could imprint characteristic signatures on escaping radiation. These effects would be extraordinarily subtle, requiring spectrographic precision that pushes our instruments to their theoretical limits. The polarization of starlight passing near gravastars presents another avenue for detection that researchers have only recently begun to explore. The quantum vacuum effects within the core could influence electromagnetic propagation in ways that rotate the polarization plane of passing light beams. This rotation would follow patterns determined by the internal structure of the exotic matter, creating a kind of cosmic fingerprint that could distinguish gravastars from their black hole counterparts. Recent theoretical work has revealed that the accretion processes around gravastars might produce distinctly different spectral signatures from those observed around black holes. As matter spirals inward toward the exotic surface, it would encounter gravitational field gradients that differ from the smooth space-time curvature around black hole event horizons. These differences could manifest as subtle variations in the X-ray emission patterns that characterize active feeding episodes. The timing of these X-ray flares carries information encoded in the gravitational field structure very close to the compact object. Sophisticated timing analysis techniques, originally developed for pulsar studies, could potentially detect the characteristic signatures that would betray a gravastar's presence. The challenge lies in distinguishing genuine gravastar signals from the natural variability that characterizes all astrophysical systems. The magnetic field configurations around gravastars would fundamentally differ from those around black holes due to the presence of a physical boundary where field lines could anchor. This anchoring would create stable magnetic structures that could persist for extended periods, unlike the dynamic field configurations around black holes where magnetic reconnection events continuously reshape the magnetosphere. These stable configurations could produce distinctive radio emission patterns that might be detectable with next-generation radio telescopes. The gravitational microlensing effects produced by gravastars would create caustic patterns subtly different from black hole lensing. When a gravastar passes between Earth and a distant background star, the exotic matter shell would introduce additional complexity to the lensing geometry. The resulting light curves would contain fine structure that could potentially be resolved with high-precision photometric monitoring campaigns. These microlensing signatures become particularly interesting when considering the galactic population of compact objects. If a significant fraction of objects we currently believe to be black holes are actually gravastars, the statistical analysis of microlensing events could reveal systematic deviations from black hole predictions. The challenge lies in accumulating sufficient statistics to distinguish between theoretical models while accounting for the inherent uncertainties in observational measurements. The implications for galaxy formation models could be profound if gravastars prove to exist in substantial numbers. The dark energy reservoirs contained within these objects would represent a distributed source of cosmic acceleration that could influence structure formation on scales from individual galaxy clusters to the cosmic web itself. Current simulations of large-scale structure formation assume that dark energy is uniformly distributed throughout space, but gravastar physics would introduce localized concentrations that could create entirely different evolutionary pathways. The feedback mechanisms between gravastar formation and galactic evolution could create complex dynamics that we are only beginning to explore theoretically. As massive stars evolve and collapse throughout cosmic history, the choice between black hole and gravastar formation could depend on environmental conditions that vary with cosmic epoch. Early universe conditions, when the cosmic microwave background provided a higher temperature floor, might have favored different collapse outcomes than we observe in the contemporary universe. These environmental dependencies could create observable signatures in the cosmic gravastar population that reflect the thermal and chemical evolution of the universe. The metallicity dependence of gravastar formation could produce correlations with galactic chemical evolution that might be detectable through statistical studies of compact object populations in galaxies of different types and ages. The quantum mechanical aspects of gravastar physics extend into realms where our theoretical understanding approaches its current limits. The vacuum condensate that would characterize the core represents a macroscopic quantum state, unlike anything we observe in laboratory physics. The coherence length of this quantum state would span stellar-scale distances, creating entanglement networks that could fundamentally alter our understanding of information processing in relativistic systems. The decoherence mechanisms that would operate in such an environment remain largely unexplored theoretically. The interaction between quantum vacuum fluctuations and the curved space-time geometry could create novel decoherence pathways that have no analogue in flat space quantum field theory. Understanding these processes could provide insights into the fundamental limits of quantum coherence in gravitational systems and the emergence of classical behavior from quantum foundations. The energy extraction mechanisms from gravastar systems could differ fundamentally from the Penrose processes that operate around rotating black holes. The presence of a physical surface would enable new classes of energy extraction processes that could tap directly into the vacuum energy reservoir of the core. These mechanisms would require exotic matter interactions that push the boundaries of known physics, but they illustrate the potential for gravastar physics to reveal entirely new energy sources. The thermodynamic properties of these energy extraction processes present fascinating puzzles for statistical mechanics. Unlike the well-understood thermodynamics of black hole energy extraction, gravastar processes would involve the quantum vacuum in ways that challenge our understanding of entropy and information flow. The possibility of extracting energy from vacuum fluctuations without violating thermodynamic principles requires careful analysis of the quantum field theory in curved spacetime. The stability analysis of gravastar configurations under realistic astrophysical perturbations remains one of the most challenging problems in theoretical physics. Real compact objects inevitably experience disturbances from infalling matter, gravitational wave emission, and interactions with surrounding electromagnetic fields. The response of the exotic matter shell to these perturbations determines whether gravastars could survive in actual astrophysical environments. Recent numerical simulations have revealed that the stability properties depend critically on the equation of state of exotic matter and the precise balance between competing forces within the shell. Small changes in these parameters can determine whether perturbations grow exponentially, leading to catastrophic collapse, or decay harmlessly over time. The sensitivity of stability to unknown physics parameters represents both a strength and weakness of the gravastar hypothesis. The observational implications of gravastar instability could provide testable predictions for distinguishing these objects from black holes. Unstable gravastars might exhibit characteristic oscillation modes that could be detectable through gravitational wave astronomy or high-precision timing observations. The frequency spectrum of these oscillations would depend on the internal structure and composition of the exotic matter shell, potentially providing direct probes of physics beyond the standard model. The relationship between gravastar physics and modified gravity theories has opened new avenues for theoretical investigation. Some approaches to quantum gravity predict modifications to Einstein's equations that could stabilize gravastar configurations under conditions where standard general relativity would predict instability. These modifications typically involve additional fields or higher-order curvature terms that become important in extreme gravitational environments. The observational signatures of these modified gravity effects could extend beyond gravastar-specific phenomena to influence a wide range of astrophysical observations. Tests of general relativity using pulsar timing, gravitational wave detection, and solar system dynamics could all potentially reveal signatures of the exotic physics that would enable gravastar formation. The convergence of evidence from multiple observational domains would be required to establish the reality of such modifications. The implications for cosmological models extend beyond the local physics of individual gravastars to encompass the global evolution of spacetime itself. If gravastars represent a significant component of cosmic dark energy, their formation and evolution could influence the expansion history of the universe in ways that might be detectable through precision cosmological observations. The interplay between stellar evolution and cosmic expansion could create feedback mechanisms that link the physics of star formation to the ultimate fate of the cosmos. These cosmological connections have motivated new theoretical frameworks that attempt to unify stellar scale and cosmic scale physics through gravastar mechanisms. Some models propose that the vacuum energy released during gravastar formation could contribute to the observed acceleration of cosmic expansion, providing a dynamic explanation for dark energy that avoids the fine-tuning problems associated with cosmological constant models. The experimental implications of gravastar physics extend into laboratory science through analog systems that could simulate aspects of exotic matter behavior. Ultra-cold atomic gases in optical lattices can be engineered to exhibit effective equations of states similar to those predicted for gravastar cores. While these analogues cannot capture the full complexity of relativistic gravastar physics, they provide controlled environments for testing theoretical predictions about exotic matter stability and dynamics. Recent experiments with Bose-Einstein condensates in engineered potentials have revealed unexpected phenomena that could be relevant for understanding gravastar physics. The formation of stable soliton structures and the emergence of effective negative pressure regions in these systems provide tantalizing hints about how exotic matter might behave under extreme conditions. The scaling relationships between laboratory analogues and astrophysical systems remain to be established, but these experiments offer valuable insights into the fundamental physics underlying gravastar models. The technological implications of confirmed gravastar existence would revolutionize our approach to fundamental physics research. These objects would represent natural laboratories where the most extreme predictions of quantum field theory and general relativity could be tested under conditions impossible to replicate on Earth. The observational techniques required for gravastar studies would drive advances in detector technology, data analysis methods, and theoretical modeling that would benefit the entire scientific enterprise. The computational challenges posed by gravastar physics have already pushed the development of new numerical techniques that combine relativistic hydrodynamics, quantum field theory, and complex geometries in unprecedented ways. These computational advances have applications far beyond gravastar research, contributing to progress in plasma physics, condensed matter theory, and computational mathematics. The interdisciplinary nature of gravastar studies exemplifies how fundamental physics research drives innovation across multiple scientific domains. The philosophical implications of gravastar physics touch on the deepest questions about the nature of physical law and mathematical truth. The emergence of these exotic objects from the mathematical formalism of established physical theories suggests that nature might realize even the most abstract mathematical possibilities under appropriate conditions. This relationship between mathematical structure and physical reality continues to challenge our understanding of why mathematics proves so effective in describing the natural world. The educational impact of gravastar research extends beyond professional physics into public understanding of science and the nature of theoretical investigation. These objects exemplify how theoretical physics can reveal possibilities that stretch our imagination while remaining grounded in rigorous mathematical analysis. The process of theoretical prediction, observational testing, and model refinement that characterizes gravastar research illustrates the scientific method operating at the frontiers of human knowledge. The international collaboration required for gravastar research has fostered scientific partnerships that transcend national and cultural boundaries. The theoretical complexity and observational challenges demand expertise from diverse scientific communities, creating networks of collaboration that advance not only gravastar physics, but also the broader enterprise of fundamental science. These partnerships serve as models for addressing other complex scientific questions that require coordinated global effort. The timeline for resolving fundamental questions about gravastar existence depends on technological advances that are already in development. The next generation of gravitational wave detectors will achieve sensitivity improvements that could definitively distinguish between competing theoretical models. Space-based observatories with unprecedented angular resolution could detect the subtle electromagnetic signatures that would confirm or refute gravastar predictions. The convergence of multiple observational approaches creates opportunities for breakthrough discoveries that could transform our understanding of cosmic architecture. The combination of gravitational wave astronomy, high-resolution imaging, precision spectroscopy, and theoretical modeling represents a new paradigm for investigating exotic phenomena that pushes the boundaries of what we can learn about the universe. The broader implications for fundamental physics extend into questions about the unification of quantum mechanics and general relativity that have challenged physicists for decades. Gravastars represent natural testing grounds for theories of quantum gravity, providing concrete predictions that could guide the development of more complete theoretical frameworks. The success or failure of gravastar models could provide crucial insights into which approaches to quantum gravity are most likely to succeed. The connection between gravastar physics and string theory remains largely unexplored, but could prove crucial for understanding whether these objects can actually form under realistic conditions. String theory provides mathematical tools for describing exotic matter states and higher dimensional effects that could stabilize gravastar configurations against instabilities that would otherwise lead to collapse. The extra dimensions and additional symmetries predicted by string theory could provide the theoretical framework needed to make gravastar formation not just possible, but natural. The experimental signatures of string theoretic effects in gravastar physics could provide some of the first observational tests of string theory predictions. The energy scales and field strengths involved in gravastar formation approach regimes where string scale physics might become observable, offering potential windows into physics beyond the standard model. These connections illustrate how gravastar research could bridge the gap between abstract theoretical physics and observational reality. The implications for our understanding of information and computation in relativistic systems could be revolutionary if gravastars prove to exist. The quantum entanglement networks that would characterize gravastar cores could represent natural quantum computers of unprecedented power and coherence. Understanding how information flows through these exotic quantum states could provide insights into the fundamental limits of computation and the nature of quantum information processing in gravitational environments. The relationship between gravastar physics and the black hole information paradox continues to evolve as theoretical understanding advances. The absence of event horizons in gravastar models provides natural mechanisms for information preservation that could resolve some of the deepest puzzles in quantum gravity. However, the exotic matter states required for gravastar formation introduce their own informational complexities that remain to be fully understood. The observational campaigns designed to search for gravastar signatures represent some of the most ambitious projects in modern astronomy, requiring coordination between space-based and ground-based facilities operating across the electromagnetic spectrum. The multi-messenger approach to gravastar detection exemplifies how contemporary astrophysics integrates diverse observational techniques to address fundamental questions about cosmic architecture. The data analysis techniques required for gravastar identification push the boundaries of statistical inference and signal processing. The subtle signatures that would distinguish gravastars from black holes exist at the very edge of observational sensitivity, requiring sophisticated algorithms that can extract meaningful signals from complex datasets while avoiding false positive detections. The development of these analysis methods contributes to advances in machine learning, statistical physics, and computational science. The scientific legacy of gravastar research extends beyond the specific question of whether these objects exist to encompass broader lessons about the relationship between theoretical prediction and observational discovery. The careful investigation of exotic theoretical possibilities illustrates how fundamental physics progresses through the systematic exploration of mathematical consequences, even when the phenomena under investigation lie at the very limits of observational accessibility. As we continue to probe the deepest mysteries of cosmic architecture, the gravastar hypothesis serves as a reminder that the universe consistently harbors possibilities that challenge our most basic assumptions about the nature of matter, energy, and space-time. Whether these exotic objects ultimately prove to exist or remain forever theoretical, they have already succeeded in expanding our conception of what physics might discover in the most extreme environments where quantum mechanics and general relativity converge into something entirely unprecedented. The quiet revolution in our understanding of compact objects unfolds through the patient accumulation of theoretical insights and observational evidence that slowly reveals the true nature of these cosmic enigmas. In this careful process of scientific discovery, we edge closer to answering fundamental questions about reality itself, guided by mathematics toward truths that may prove more extraordinary than we have ever dared to imagine. The countdown to discovery accelerates with each passing moment, as astronomers prepare to deploy observational techniques so precise they could finally reveal whether we share our galaxy with objects that fundamentally challenge everything we thought we understood about the nature of reality itself. The next decade promises to bring us face to face with possibilities that could either confirm our current understanding of cosmic architecture or shatter it entirely. The theoretical predictions for gravastar detection have reached a level of sophistication that allows researchers to specify exactly what future observations should reveal if these exotic objects truly exist. The gravitational wave signatures from inspiraling compact objects would carry information encoded in the precise timing of orbital decay, the frequency evolution of the gravitational wave chirp, and the post-merger oscillations that characterize the final moments of cosmic collision. When two gravastars spiral together and merge, the collision would produce gravitational waves with characteristics that differ measurably from black hole mergers. The exotic matter shells would create additional oscillation modes that would persist longer than the simple ring-down expected from black hole collisions. These extended oscillations would carry the fingerprints of exotic physics, creating observational windows that could last for minutes, rather than the milliseconds typical of black hole mergers. The European Space Agency's LISA mission, scheduled for launch in the mid-2030s, will possess the extraordinary sensitivity needed to detect these subtle differences. Operating in the vacuum of space, free from terrestrial vibrations and gravitational noise, LISA will monitor gravitational waves across frequency ranges inaccessible to ground-based detectors. The mission's 3 spacecraft, separated by millions of kilometers, will create an interferometer so sensitive that it could detect gravitational wave amplitudes smaller than the width of an atomic nucleus. The data analysis challenges for LISA observations will push computational physics into entirely new territories. The gravitational wave signals from gravastar mergers would require theoretical templates that incorporate exotic matter physics, quantum field theory in curved spacetime, and the complex dynamics of shell oscillations. Creating these templates demands some of the most sophisticated calculations ever attempted in theoretical physics, involving numerical relativity simulations that must track exotic matter behavior under extreme gravitational conditions. The statistical significance required for claiming a gravastar detection would need to meet the most rigorous standards in scientific history. The implications of such a discovery would be so profound that the evidence would need to be overwhelming and independently confirmed through multiple observational channels. This standard creates both opportunities and challenges for researchers, demanding unprecedented precision in both theoretical predictions and observational analysis. The electromagnetic signatures that could distinguish gravastars from black holes continue to evolve as theoretical understanding advances. The quantum vacuum effects within gravastar cores could influence the propagation of light and other electromagnetic radiation in ways that create subtle but detectable modifications to observed spectra. These effects would be most pronounced for radiation that originates very close to the exotic matter shell, where the influence of the quantum condensate would be strongest. The polarimetric signatures of gravastar environments represent one of the most promising avenues for observational discrimination. The exotic matter shell could interact with electromagnetic fields in ways that create distinctive rotation patterns in the polarization of escaping light. These polarization effects would follow mathematical relationships determined by the internal structure of the gravastar, potentially providing direct observational access to the exotic physics occurring within these hypothetical objects. Future space-based telescopes with unprecedented angular resolution could potentially resolve the surfaces of nearby gravastars, revealing features that would be impossible around black holes. The James Webb Space Telescope and its planned successors will achieve resolution capabilities that approach the theoretical limits imposed by the wave nature of light itself. While still insufficient to directly image gravastar surfaces, these instruments could detect the thermal emission and spectral features that would characterize the exotic matter boundary. The timing analysis techniques developed for pulsar observations provide another powerful tool for gravastar searches. The precise periodicity of pulsar signals allows astronomers to detect gravitational perturbations with extraordinary sensitivity. A pulsar orbiting a gravastar would experience gravitational effects that differ subtly from those around a black hole, creating timing residuals that could accumulate to detectable levels over years of careful observation. The theoretical framework describing these timing effects involves perturbation theory applied to exotic space-time geometries. The calculations must account for the modified gravitational field structure near the gravastar surface, the influence of quantum vacuum effects on geodesic motion, and the complex interplay between electromagnetic and gravitational forces in the strong field regime. These theoretical predictions provide testable hypotheses that could guide future observational campaigns. The implications for tests of general relativity extend far beyond the specific question of gravastar existence. These objects would serve as natural laboratories for probing the foundations of spacetime physics under conditions that cannot be replicated in terrestrial experiments. The extreme gravitational fields and exotic matter states would provide testing grounds for the most fundamental predictions of Einstein's theory and its potential modifications. Recent theoretical work has revealed that certain modifications to general relativity could actually favor gravastar formation over black hole collapse under specific conditions. These modified gravity theories typically involve additional fields or higher-order curvature terms that become important when spacetime curvature reaches extreme values. The observational signatures of these modifications could extend beyond gravastar physics to influence a wide range of astrophysical phenomena. The cosmological implications of widespread gravastar existence would require fundamental revisions to our understanding of cosmic evolution. If a significant fraction of compact objects are gravastars rather than black holes, the dark energy reservoirs they contain could influence structure formation on scales from individual galaxies to the cosmic web itself. The feedback between gravastar formation and cosmic expansion could create dynamics that link stellar-scale physics to the ultimate fate of the universe. Computer simulations attempting to model these large-scale effects face computational challenges that push current supercomputing capabilities to their limits. The calculations must simultaneously track the formation and evolution of individual gravastars while modeling their collective influence on cosmic structure formation. These simulations require new numerical techniques that can handle physics across an enormous range of scales, from quantum mechanics within gravastar cores to general relativistic effects governing cosmic expansion. The relationship between gravastar physics and dark matter research has opened new theoretical avenues that could revolutionize our understanding of cosmic composition. Some models suggest that dark matter particles could accumulate preferentially within gravastar cores, where they would interact with the exotic vacuum state in novel ways. These interactions could produce observable signatures that would simultaneously reveal the nature of dark matter and confirm gravastar existence. The particle physics implications extend into the deepest questions about fundamental forces and the unification of physics beyond the standard model. The extreme conditions within gravastar cores could activate symmetries and interaction mechanisms that remain hidden at lower energy scales. Studying these effects could provide natural laboratories for exploring physics that would otherwise require particle accelerators far beyond current technological capabilities. The experimental approaches to gravastar physics have expanded beyond astronomical observations to include laboratory studies of analog systems. Ultra-cold atomic gases can be engineered to exhibit effective equations of state, similar to those predicted for exotic matter. While these laboratory analogues cannot capture the full complexity of relativistic gravastar physics, they provide controlled environments for testing theoretical predictions about stability and dynamics. Recent breakthroughs in quantum simulation techniques have enabled researchers to create artificial spacetime geometries using trapped ions and superconducting circuits. These quantum simulators can model aspects of curved spacetime physics and exotic matter interactions, providing insights into the fundamental processes that would govern gravastar behavior. The results from these experiments help validate theoretical calculations while identifying new phenomena that might be relevant for understanding real gravastars. The technological developments required for gravastar detection have driven advances across multiple fields of physics and engineering. The precision required for gravitational wave astronomy has pushed laser interferometry to its theoretical limits, while the computational demands of data analysis have accelerated developments in high-performance computing and artificial intelligence. These technological advances have applications far beyond gravastar research, contributing to progress in fields ranging from medical imaging to quantum computing. The international collaboration required for gravastar studies exemplifies how fundamental science can unite researchers across cultural and political boundaries. The theoretical complexity and observational challenges demand expertise from diverse scientific communities, creating partnerships that advance not only gravastar physics, but also the broader enterprise of understanding cosmic architecture. These collaborations serve as models for addressing other complex scientific questions that require coordinated global efforts. The philosophical implications of gravastar research touch on fundamental questions about the relationship between mathematical possibility and physical reality. The fact that solutions to Einstein's equations can describe such exotic objects raises profound questions about why certain mathematical structures find expression in nature, while others remain purely abstract. Understanding this relationship could provide insights into the deepest principles governing the universe's operation. The educational impact of gravastar studies extends beyond professional physics into public engagement with science and the nature of theoretical investigation. These hypothetical objects exemplify how theoretical physics can reveal possibilities that challenge our intuition while remaining grounded in rigorous mathematical analysis. The process of prediction, observation, and model refinement that characterizes gravastar research illustrates the scientific method operating at the frontiers of human knowledge. The timeline for resolving fundamental questions about gravastar existence depends on observational advances that are already in development. The convergence of gravitational wave astronomy, high-resolution imaging, precision spectroscopy, and theoretical modeling creates unprecedented opportunities for breakthrough discoveries that could transform our understanding of cosmic physics. The next generation of observational facilities will achieve sensitivity improvements that could definitively distinguish between competing theoretical models. These instruments will operate across multiple messenger channels simultaneously, combining gravitational waves, electromagnetic radiation, and potentially other exotic signals to create comprehensive pictures of extreme astrophysical phenomena. The statistical techniques required for analyzing these multi-messenger datasets will demand new approaches to data fusion and signal processing. Machine learning algorithms trained on theoretical predictions could potentially identify patterns that human analysts might miss, but these automated approaches must be carefully validated to ensure scientific rigor. The challenge lies in extracting genuine signals from complex datasets while avoiding the statistical pitfalls that could lead to false discoveries. The broader implications for fundamental physics extend into questions about the ultimate structure of reality itself. Gravastars represent meeting points where quantum mechanics and general relativity converge into something entirely new, providing natural testing grounds for theories of quantum gravity. The success or failure of gravastar models could guide the development of more complete theoretical frameworks that unify all fundamental forces. The connection between gravastar physics and string theory continues to evolve as theoretical understanding advances. String theory provides mathematical tools for describing exotic matter states and higher dimensional effects that could stabilize gravastar configurations. The extra dimensions and symmetries predicted by string theory could provide the framework needed to make gravastar formation not just mathematically possible, but physically natural. The observational signatures of string theoretic effects in gravastar physics could provide some of the first empirical tests of string theory predictions. The energy scales involved in gravastar formation approach regimes where string-scale physics might become observable, offering potential windows into physics beyond the standard model that would otherwise remain inaccessible to experimental investigation. The implications for our understanding of information processing in extreme gravitational environments could revolutionize computational science. The quantum entanglement networks that would characterize gravastar cores represent natural quantum computers of unprecedented complexity and coherence. Understanding how information flows through these exotic systems could provide insights into the fundamental limits of computation and the nature of quantum information in curved spacetime. The relationship between gravastar physics and the measurement problem in quantum mechanics remains largely unexplored, but could prove crucial for understanding how classical reality emerges from quantum foundations. The macroscopic quantum coherence that would characterize gravastar cores could provide natural laboratories for studying the transition between quantum and classical behavior under extreme conditions. The observational programs designed to search for gravastar signatures represent some of the most ambitious projects in contemporary astrophysics. These campaigns require coordination between facilities operating across the electromagnetic spectrum, from radio telescopes that monitor pulsar timing to gamma-ray observatories that study high-energy phenomena. The integration of these diverse observational approaches exemplifies the multi-messenger astronomy that characterizes modern astrophysical research. The data analysis pipelines required for gravastar searches push the boundaries of computational physics and statistical inference. The signals that would distinguish gravastars from black holes exist at the very limits of observational sensitivity, requiring sophisticated algorithms that can extract meaningful patterns from noisy datasets. The development of these analysis techniques contributes to advances in fields ranging from signal processing to machine learning. As we stand at the threshold of discoveries that could fundamentally alter our understanding of cosmic architecture, the gravastar hypothesis serves as a powerful reminder that theoretical physics continues to reveal possibilities that stretch our imagination. Whether these exotic objects ultimately prove to exist or remain forever in the realm of mathematical speculation, they have already succeeded in expanding our conception of what the universe might contain in its most mysterious and extreme corners. The search for gravastars embodies humanity's deepest quest to understand the fundamental nature of reality, pushing the boundaries of physics into regimes where quantum mechanics and gravity merge into something unprecedented. In laboratories and observatories around the world, dedicated researchers continue to probe the mathematical structures that govern cosmic behavior, seeking answers to questions that touch on the most profound mysteries of existence itself. The quiet revolution in our understanding of spacetime unfolds through the patient accumulation of theoretical insights and observational evidence, gradually revealing the true nature of these cosmic enigmas. In this careful process of scientific discovery, we edge ever closer to answering fundamental questions about the universe we inhabit, guided by mathematics toward truths that may prove more extraordinary than we have ever dared to imagine. The quiet accumulation of evidence continues across multiple observational channels, each dataset adding another piece to a cosmic puzzle that could redefine our understanding of the most extreme objects in the universe. In radio observatories scattered across remote mountaintops and desert plains, astronomers monitor the precise timing of pulsar signals with accuracy that defies comprehension. These cosmic lighthouses, spinning neutron stars that sweep beams of radiation across space, serve as natural laboratories for testing the fundamental predictions of general relativity. When a pulsar orbits a compact companion, the gravitational waves generated by this cosmic dance gradually rob energy from the system, causing the orbital period to decay at precisely calculable rates. Einstein's equations predict this orbital evolution with mathematical precision that's been confirmed to extraordinary accuracy. But if some of these companions are gravastars rather than black holes, the subtle differences in their gravitational field structure could create timing residuals that accumulate over years of careful observation. The challenge lies in distinguishing genuine gravastar signatures from the countless other effects that influence pulsar timing. Interstellar plasma variations, planetary motions within our own solar system, and even the slow drift of Earth's rotation all contribute noise that must be meticulously removed from the data. The signal processing techniques required for this analysis represent some of the most sophisticated ever developed in astronomy, capable of detecting timing variations smaller than a few nanoseconds accumulated over decades. Tonight, as we reach the end of our journey into the deepest mysteries of cosmic architecture, we find ourselves standing at the threshold of questions that may reshape everything we thought we knew about reality itself. The gravastar hypothesis represents more than just another exotic theoretical possibility. It embodies our species' relentless quest to understand the fundamental nature of existence, pushing the boundaries of mathematics and observation into realms where quantum mechanics and gravity converge into something entirely unprecedented. Whether these extraordinary objects exist somewhere in the darkness between the stars, or remain forever in the realm of mathematical speculation, they have already transformed our understanding of what might be possible in the most extreme corners of the universe. In laboratories and observatories around the world, dedicated researchers continue their patient search for answers, guided by equations toward truths that may prove stranger than we have ever dared to imagine. The universe keeps its secrets well, but human curiosity burns brighter than the most distant star. And in that burning curiosity lies our greatest hope for finally understanding our place in this vast, mysterious, and potentially far more exotic cosmos than we ever dreamed possible.